Okay, so I think I'll make a start, and it's our great honor to have Anu here and from MIT. I don't really think she needs any introduction at all, but just for for more information, and she's a founder and director of the Active Adaptive Control Lab in Department of Mechanical Engineering at MIT. Her research interests span adaptive control and its applications to aerospace, automotive, propulsion, and energy system, as well as cyber-physical system. She has received a large number of recognitions, including numerous Best Paper Awards and IEEE Fellow, IFAC Fellow. She has made significant contributions serving our society. Well, she was the president of IEEE Control System Society, and she served as editor, associate editor for many, many journals. And together with colleagues, she has drafted a large number of very, very influential reports in this area, including the impact of control technology and also control for societal scale challenges, Roadmap 2030. She's currently serving as the president-elect of American Automatic Control Council, and she will serve the editor-in-chief of IEEE Control System magazine from next January. So without further delay, Anu, time is yours.
Well, thank you, Bing, for that very, very kind introduction. It's really an honor to come home, so to speak, to this technical committee on adaptive systems. So I'm really looking forward to sharing some of my thoughts today with you all, and hopefully there'll be time for a couple of questions afterwards. This, I think, is supposed to work. Okay. All right, can you see my screen now?
Yeah.
Yes,
we can.
Good.
Thank you.
Yeah.
You can see the screen, right? Because I cannot see you the way my PC is set up. So, okay, all right, please speak up, and if you need to interrupt me, and then we'll go from there. Okay, all right. So again, like I said, this is really an honor and a privilege for me to speak with you all, and on a topic that I really love. I've been working in this area for the past, I don't know how many decades, but I still feel like I've only scratched the surface and there's so much more to do and research. So I want to share with you some of the highlights of this particular topic. So this is the overall introduction, and again, I'll keep coming back to this, so I'm not going to dwell on it. So what we're all trying to do here, all of us in the systems and control community, is to really figure out how we can take some real-time decisions that allows these systems to approach some desired goals. And typically, depending upon the time scales at which these things happen, there is like some sort of an inner loop decision making, and then there's an outer loop decision making, which gets to be broader and looking a little bit more ahead and towards the goals, towards the path, or towards a trajectory. And the point always is that we want to be able to do that, because not only is there dynamics, which means there's a lag between the time you take an action and for it to really result in a result, and also you have to meet all kinds of uncertainties that may happen at any time, and therefore you have to contend with those kinds of modeling errors, perhaps. And also you have to really honor the constraints that you have in the actual system. So all of these things basically make the problem challenging. And so you have to make sure, first of all, that everything stays firm. And the second thing is that even when you shake it, when you have all kinds of disturbances and other perturbations, it stays robust. And you stay safe, that you really don't wander into regions that are not desirable. And all the time you want to make sure that some sort of an effort is minimized, some sort of a cost is minimized, some sort of a performance is optimized. And of course, the challenge always is that you want to be able to do this in a way so that you accommodate uncertainties and you meet constraints. And so as a community, we've been at this for a long time. And so we do a lot about what happens in the inner loop. This is basically the definition, the origin of how control was defined, and these are the kinds of system properties that we worried about. And so if you look at the story of all the way from water clocks and flyball governors to control of physical systems, and we talk about a whole bunch of the footprint, the loci of control in a variety of applications, and moving from physical domains of aerospace and automotive and process and healthcare and robotics and manufacturing. We are expanding the scope of where controls can play a role, because we really look at what happens in the intersection, in the nexus between the physical and the digital worlds, and that allows us to really have a handle on these kinds of large systems in a large canvas, which really brought the conversation to the document that being mentioned, which is that not only are we limited to engineering systems, but really problems that are driven by the societal needs. And let's just sort of remind ourselves that this is sort of the real framework, the broad framework within which we operate. So the story that I want to tell you is sort of my journey into this grand canvas, and the kinds of things that I find to be fascinating, and all of which is really in the context of adaptation. So if you're going to have uncertainties that really occur in real time that you cannot anticipate, and there are actuators that lose their effectiveness, and there are other kinds of modeling uncertainties, then how do I really figure out a way in which you can design this real-time control using whatever measurements that you have and from data, so that everything here is data-driven, and whatever prior information you have about the model structure. So I want to basically articulate first, and please bear with me if this is a tutorial thing somewhat in the beginning. And again, I was trying to figure out how to, gauge what kind of audience I'm going to get. So I think some of you can probably put me on mute, because I'm just going to talk about some of the tutorial things and then go on to adaptation and safety and adaptation and optimality. So the basics of control really is about designing the control input in real time so that your state variables and your outputs behave in the way that you want. But what is unique about it is that we have these learning algorithms as a part and parcel of what we do. And these are, of course, provably correct. And what this provides is not only a way of designing the control input, and essentially you come up with these functions C1 and C2, but you also have a way of learning what's going on. And if it is indeed parametric uncertainties, then the parameter estimate theta hat is basically something that learns what's going on. So while you might do control in a faster time scale, with hindsight, you do want to learn. So that's really the goal. So let me walk you through, in case there are students who are listening to adaptive control for the first time, this is for you. So if you have a simple first order system, and the name of the game here is that AP is unknown, and you're trying to design a way in which you can control it, and you've set up what's known as the reference model, and you look at the error to say, hey, is it possible to minimize this error in some way by adjusting the estimate of what you want in the feedback loop, which leads to an error equation? Normally, what we would do is to really adjust the cost function J and look at the gradient. And of course, we use a gradient descent approach and all of these things, but it's not possible for us to always make sure that it'll lead to the to a minimization, because a cost function might not look like this. And it turns out that you can still come up with a way in which you figure out what the right algorithm is. And because ideally you would like, for instance, in this particular case, to have access to E prime, which is the signal that is driving the error, but you don't have that. And so if you were to use this, and of course, this is, there are lots of work that's been done in the extreme seeking literature that tells you different ways in which you can get around it. But the basics of adaptive control really started out with, hey, what happens if you were to do something like this? And the reason why this works is because not only are you able to design this controller, but you're able to provide a stability framework that says that there is some sort of a energy function, a positive definite function that is going to be non-increasing. And so, hey, you have your foundation right. And we can extend this to when you have all the states accessible. And of course, your Lyapunov function gets a bit more complex. But the idea here still is that you can design a state feedback where you're adjusting the parameter and feedback loop. We can do that when only some of the states are available, and you use the notion of a strict positive real operator, and then you can use the notion of augmented error, or there's a variety of different tools right now available. One can use backstepping, with systematically laid out ways in which you can figure out how all of the different parameters that allow can be adjusted when you have a large relative degree between the input and the output. And of course, all of these things can be extended to when you have unknown nonlinearities. And so this is, again, just a very, very simple example. And Mirslav's book really details it very well in terms of what you can do if you don't have feedback linearizing structures. But if you do, then the idea simply is that the adaptive nonlinear control tries to estimate the parameters, and you can come up with ways in which the parameter estimation can be done, and again, provide guarantees. And so there is also a link between what one can do between these kinds of things and neural networks. And so if you start with a simple linear single layer network, then basically they become coincident. And again, like I said, there's lots of other ways, structures that have been laid out very nicely. And one can take all of these things as a basis and then introduce other kinds of uncertainties now into the problem, which are not parametric, in which case you're not really be able to adapt to them, but you accommodate them using robustness ideas. And so here, the notion is that you have some sort of a baseline controller, but then you might have actuator uncertainties because the actuator has some sort of a lag, or there are other model dynamics. And there are ways in which we can guarantee that there is robustness to these kinds of uncertainties as well. Okay, so let's just focus a little bit on learning. And again, like I said before, learning is part and parcel of adaptive control, which sort of distinguishes it from some of the other methods that don't necessarily have an explicit learning component. And so the idea here is basically that while you are after a certain performance error, you're also trying to learn the parameter. And so the parameter error gives you a way of the parameter estimation algorithm gives you a way of learning these uncertainties. And so the effect of parameter learning is clear, because if you use even a simple damping ratio and natural frequency, even if you were to perturb it a little bit in the parameter space, the impact of it in the state is enormous. And therefore, you really want to have real-time decisions that allow you, with hindsight, to learn the parameters. And ultimately, what it gives you is a robustness guarantee, and which has been actually, again, documented in several papers over the years. And again, I'm happy to have an offline discussion if there's more questions on this. So how does this happen? How do you actually guarantee that you can learn? Then you basically invoke the concept of persistent excitation that says that if you have these properties that where whatever is driving your parameter adaptation, which is some sort of a regressor that consists of key variables in the feedback loop, if there is a certain uniform observability property, there is a linear independence in the data that you're getting, there is some excitation in the data that you're getting that allows you to probe all of the modes of the system, then that allows you to get to learning. And what is great about this is that this is not just a sufficient condition, but it is necessary, which means that if you don't have it, you really cannot have learning. Now, excitation means that your exogenous signals, your command signals, whatever is extraneous to the feedback loop, needs to have these properties of excitation, which is also known as exploration in the machine learning world. So now, if you can't do that, if that is counter to what your mission goals are, your system goals are, then you have a problem, which is that you really are not able to learn, right? Which brings us to imperfect learning. So it is possible that performance and learning, in some cases, are conflicting objectives, which means because it's a necessary condition that you have excitation, if you don't have excitation, you have to acknowledge the fact that you can have imperfect learning, right? So the question here, and let me just make the point using a flight control example. Let's assume that there is a parameter, and if you are indeed at the true parameter, then your system performance, and in this particular case, it's an angle of attack story, and the angle of attack has to basically come down to 0, because you want to make sure that the aircraft basically has a desired thing, doesn't go into stall, and all of that stuff. Now, if for whatever reason you've got uncertainties in the problem, so then what you think is that what is the true parameter that you should have put in the controller is not it anymore. Theta 1 would have been good if the system performance was nominal, but now the operating condition has moved away from the nominal, and so the correct parameter that you need to put is not theta star, it's not theta 1, but theta 1 plus delta. But if that happens in the system space, you are totally off, because these things, in this particular case, it's a blended wing body vehicle, and what it has is basically all kinds of shock distributions, and it's very easy to construct an example where this happens. So which means that you need to learn what the correct parameter is, right? So here you have a real challenge. So what do? Well, I try to get to the, obviously I don't want the blue, I want the black. And so how do I get there? And so this is basically what adaptive control can do, which is one of the most fascinating properties that is why I guess I'm still working in this area after several decades, because you don't necessarily get to the true parameter, but adaptive control tells you a way of getting to something which is such that as far as the projection of those parameter errors, the learning errors in the performance space is basically 0. And because you're in that null space, you're okay, and you can accomplish imperfect learning, even in the presence of imperfect learning, safe performance. And this is a very, very important point that is really missed by a good part of the machine learning community, unfortunately. So you have to keep in mind, therefore, so what happens? Again, there are some excellent papers that Brian Anderson has articulated, which gets into a lot of the details, but here is the main idea. Suppose I have a scenario where I have a reference signal which does have excitation, right? So then what happens is that if you look at the underlying loss function that you're trying to minimize, it does go to 0. And if you look at the learning error, that also goes to 0, correct? So this is all with learning. But what happens if you don't have learning? So then here is a case where I don't have the luxury of having this exploration. And so what happens is that, so imagine, this is just an example, right? It's an academic example. So in this particular case, I have to think of this 20 as sort of infinite time. So I'm I'm basically applying this signal, and I see that this loss function nicely goes to 0. I think that all is well, right? But then the learning error obviously has not gone to 0, and therefore now you have a problem of this bursting phenomenon. Why? Because suppose now you introduce new frequencies because there is a step, then the loss function has to readjust. So you can see that here is another kind of a burst of information, and therefore it readjusts. And so yes, the learning error goes down, but then every time you see a new excitation component that comes into the picture, you basically have to repeat this bursting. This bursting phenomenon repeatedly occurs until your learning error fully goes to 0. So this is something that one really has to keep in mind. And if you have some scenario that you've not really seen before, and in this particular case, because you're only exposing the system to signals of a certain frequency, every time you introduce a new frequency, you're going to see this phenomenon, and this is something that one really has to be careful about. Okay, so that's the point here with imperfect learning. So now I want to maybe spend about, I'm going to rush through this a bit, just 5 minutes on sort of the closed notion that's been hanging around us. And those of you who have not perhaps seen this connection, I want to sort of introduce that, which is to say, what exactly is reinforcement learning, and how does it relate to whatever we're talking about? So it turns out that there's something very, very, very similar. And so while the structure and the context and the overall framework and the tools used are different, the ideas have a lot of similarity and interconnection with what we're trying to do in here. So let's suppose that you have an environment and you have an agent, and what you're trying to do is to maximize some sort of a value function. So the environment is very unstructured, so you use, instead of a deterministic structure, Markov decision process. So what you're trying to do is very much built on optimality, and if you think of adaptive control as something that's built on stability. So what you're trying to do is to basically maximize this value function, which has to do with rewards. And the current reward is more important than the past. And so you set up this kind of a weighted average of all of your rewards. And so the policy is something that basically maximizes this. And so in order to do this, you say, okay, and sometimes it turns out that you can make the problems more tractable using this notion of a Q function. And so what you try to do is to look at the reward now and look at the past rewards, and then this Q function allows you to come up with the optimal policy as well as the optimal value function. Now, the connection between that really lies in the nonlinear optimal control. And again, Miroslav's Bodhi lecture articulated many of these interconnections very elegantly. So if you have an unknown nonlinear system and you've got this infinite horizon cost, then the optimal cost to go basically is determined by the infimum of this cost. I'm just turning the problem around, whether you think of it as a maximization or minimization, which leads to the very well-known HAB equation that says that, the optimal policy is the one that basically comes up with the infimum of this. And therefore, the argument is basically the one that gives you the optimal controller. So reinforcement learning is all about learning the policy function or learning the value function, right? So the problem basically is when you bring in the uncertainty. So everything is certain and you know everything that's going to happen and all of these different transitions, and therefore you can evaluate the cost across each of these different branches, then it's great. And you can use the notion of dynamic programming, which gives you a very elegant solution for HAB equations. But the problem basically comes in when you have uncertainties. So now all of these value functions and everything have to be replaced by their estimates, which is where neural networks have really come into the story, which again brings in a parametric structure. And the moment you bring in a parametric structure, there are all kinds of parallels to adaptive control. So in this particular case, what we're trying to do is to say, hey, I don't know something, which is the value function or the policy function. Use a neural network to approximate it. And in order to do that, what do? You come up with some sort of a parametrization of that structure. And the nice thing about it is that there is a very nice basis of universal approximation that says that, yes, if you use these activation functions and several layers, and the deeper it is, you have a deeper learning. And so all of this gives you a way of approximating any arbitrary nonlinearity. And you basically estimate the weights by using, again, this very well-known gradient approach that we've been talking about, which brings in this notion of a backpropagation algorithm. So it turns out you can do all of these approximate policy iterations and so on, and iterative procedure. But I want to focus on basically a couple of examples of, if you take all of these things, you can come up with analytical guarantees. And so this is one that we did, again, more than 2 decades ago, where we say, okay, the problem is here is a nonlinear system, and I'm trying to come up with a controller. And so let us suppose that I do use something like this neural network. Then is there a way in which I can come up with an adjustment procedure? And this problem is extremely difficult and is really open, and nobody has been able to come up with a complete, accurate solution to this problem. And so the reason is that the problems of non-convexity have to be addressed, and the stability of adjusting the nonlinear weights addressed, because even though W2 might be linear, W1 is not, and that's where the difficulty comes in. And there are all kinds of errors of approximation. I'm not going to go into the details, but basically what we were able to show was that if you use this neural control, you can come up with a Lyapunov-centric approach for training the weights, because what you do is to basically look at the corresponding derivative, and you basically pick a desired target, and you can then use this difference between the desired target and the actual derivative as a loss function. And when you introduce this kind of a training procedure, you can come up with a guarantee that this neural network-based control can give you stability. So it's one of the few results that basically tell you that you can use this neural network and guarantee that locally you are able to get an approximation. So the nice thing about it is that you can really look at very nasty nonlinearities, and it gives you a way of actually coming up with a neural controller. And it is the added advantage if you were to just linearize it, and because we said it's a local result. If it's local, hey, why not use a linear system? But we can clearly show where the adjustment from the neural controller comes in, so that it really expands the scope of what you can do, and that's very clear. There's also been other interesting results or ways of looking at this problem. And here is one that I find to be particularly compelling, that says that if you have these extra uncertainties in the form of this nonlinearity G, you can still design the input and have an optimal policy. And the optimal policy basically comes out of this particular inequality that you need to minimize. And the nice thing about it is that the way this is structured, the cost function is picked in a way so that it's not just optimizing it from minimizing a cost function from an optimality point of view, but basically integrating it with a stability point of view that says that the all of the solutions that you find for your policy should be such that the correspondingly optimal function candidate basically is inside a level set. So by doing this, they were actually able to essentially guarantee. So this is basically the whole world of safe reinforcement learning that says that if you, this kind of a structure allows you to basically make sure that you stay within a domain of attraction for a certain region of initial conditions. I mean,
sorry,
this is a world. Sorry, is there a question?
Yeah, sorry, Anne. So if you look at the screen, at the bottom, there's Teams. So team is sharing screen, stop sharing, hide. Can you click hide?
Okay, got it. Thank you.
Yeah, thank you.
Okay, I didn't know what to do with it. I thought I was seeing it only at my end. Thank you, Bing. I really appreciate it. Okay, all right, apologies for that. Okay, all right. So this is, and then they also provide a nice implementable training procedure, but you have to keep in mind that the tools that have been proposed for stability are not often not exactly the same as the tools that have been shown to be very successful and doable and implementable. And so there is a big gap there between what is analytically justified versus what actually goes on in terms of the practical implementation tools. So all of this basically is what I wanted to say in terms of adaptation and learning, and I hope that you see the rich intersection and the integration between these concepts that are really joined at the hip. And there's so much more to do to really understand how these things can be played. But I want to now move on to other systems goals, and the two things that I want to talk about are safety and optimality. So let's start with safety. So we're really talking about state constraints. So there are any number of problems where you really want to make sure that you meet a certain performance, but at the same time, really make sure you do not wander into unsafe regions, right? So in the context of a cruise control, you want to follow a lead vehicle, but you want to make sure that you always maintain a certain distance D. So anything where your position is less than D is unsafe. Same thing with aerial vehicles. If you have a missile dynamics, you don't want to stall. And so, but at the same time, you want to meet whatever your performance goals are. Robotics, obstacle avoidance, and you want to, again, reach your goal and your target within a certain time, hopefully optimally, but you want to make sure that you don't hit any obstacles. So there are all of these kinds of problems that says that anything that you're trying to do has to meet safe constraints, and it's not easy to do that, right? Because if you only, let's say that you're looking at theta and theta dot as the state variable, and here's a phase variable plot on the left side. So if you really only look at just the baseline and the ellipse is the safe region, then you can start somewhere because you really don't know these level sets in terms of performance. So you wander and you go way outside and you come back. And obviously, this is not something that you want. It's not a good idea. Whereas it is possible as you learn and integrate some of the key pieces. And one of the tools that has become highly popular is what is known as control barrier functions that has come out recently. And so these then allow you to learn how to be safe, right? So that's really what we're after. So let's now bring in the problems that we've looked at now. And so say, hey, is it possible for us to do both, have performance and at the same time remain safe when you have real-time uncertainties? That's the challenge here. And how do you meet these two things? So in fact, here there's a sort of a more philosophical journey one can take, which is that real-time decisions, things that we do in adaptive control often are one kind, and those that come out of CBF types of designs are another kind. And you can argue that the ones that we're trying to do is always predicated on a structure of a model, whereas the computational control pieces come from model-free kinds of things. Let me explain. So one of the examples that we did, and I'm going to skip the video, not play it here, but play it later, is that here is a closed form example of a closed form thing. So in this particular case, it was a quadrotor, and basically here is a structure that we imposed on the controller. we stuck our neck out and said, hey, you know what, for whatever reason, I'm going to have a state feedback structure. And as far as I'm concerned, I'm going to search within the manifolds that is determined by this closed form expression. And here is basically how I'm going to carry out the adaptation. And it turns out it works. Again, I'll show this. Sorry, I'm going to show it later. So computational control, on the other hand, says, I'm going to come up with a real-time decision which basically spits out the control input, and it has to be such that it satisfies this implicitly. I minimize something subject to something, right? So that I would put this under a computational control thing where you're not asking for a whole lot of information or imposing assumptions on what F and G and all look like, but you're basically saying, hey, if this is satisfied, then I have a safe way of going forward. So the question is it possible to combine these two? And we've started this process, and this is, again, just a recent result from our group, which says, yes, here is a way to do this. And this is sort of how the structure looks like. And so the idea here, and there is a lot of stuff, things going on here, everything in this block in here is adaptation based. And where we basically bring in elements from CBF is basically in the outer loop. But there are some very key integrative pieces that have to come in. And one comes because you introduce some bells and whistles in the reference model. And another one comes in because you introduce some important additions to the CBF filter itself. And when you do all of those things, and the structure basically looks like this, and here's some of the technical details. So when you have uncertainties in the plant, and you have input constraints also, then it turns out that this is how you can stitch together control, adaptive control, and the control barrier functions. And let me just give you some examples. And again, the technical details, I will let you peruse the CDC paper. So what's the goal here? It's a very simple Mickey Mouse type of example. I want to start wherever I am and end up with this target. And I don't want to make sure that I don't hit the obstacles. It kind of is not really doing it here, because if you look at very close, zoom in and look at the boundary, you're kind of transgressing and you're on the wrong side of the dashed lines. And because you're doing that, then obviously you kind of are playing, there's this close skirmish with stability, it's with safety. So you don't want that. So remember, I told you there's this thing called EBR, which is error-based relaxation. I don't really have that here, but when I introduce the EBR, then it turns out that I can indeed have my performance goal met in the presence of adaptation, in the presence of parametric uncertainties. By the way, this particular first order example has uncertainties, so even with that, I'm able to do it. So then the question that I asked Johannes is that, hey, what happens if you had other kinds of starting points? And it was really cool to see what happens, because the algorithm automatically figures out the appropriate path to make sure that you stay safe and still meet your stability goals. Your performance goal, which is really to go to the target, all the time making sure that you're stable. So this was really very satisfying. So we then looked at other examples. So here is a double integrator, which is more realistic. So on the left side, you've got the classical controller. And so the goal here is that you always stay within these dashed lines. And whereas on the right side, we introduced also the CCBF. And so you can see that on the right side, I have both safety and stability, whereas on the left side, I do not. And so this is something that, again, we went as far as we could in terms of having a practical demonstration, but by using high fidelity hardware in the loop type of tools in here, which is the Simulink desktop real-time emulator. So, and here's really what happens in this particular case. We actually have okay, now it's the same thing that you saw there. You stay within this green shaded region, and what you see are the two states on the left side, the control input on the right side, and the axle parameter adaptation in the bottom right corner. So that really is another example. We then took it further and made it multivariable. Hey, what if you have a 6-stop quadrotor, which basically has a much higher relative degree? And so we then came up with the CBF structure as well as the adaptation. So let me just walk you through the examples in here. So the idea here is that what you're looking at on the left side is the top view, and what you're looking at is the elevation. And so you need to always stay inside that rectangle at the top left corner here. whereas you have to stay between the ellipse and this rectangle in the elevation in here. So this particular trajectory is not doing any of those things because there is no adaptive controller, there is no CBF, and so obviously it crashes and it becomes unsafe and all of that. And so, and the thing that keep in mind, this is a quad rotor, right? Because there are many, there are four rotors, there are the four inputs. We introduced a loss of effectiveness in the, as you're facing it, the middle one and the right one. So it's an asymmetric loss of effectiveness. And so obviously there is a lot that we are not able to do. So we now introduced CBF, and so which says now that, yeah, okay, the actual reference trajectory that you're trying to follow, which is really the blue, is good. That's safe. But because we have no adaptation, there is no way in which it can do it. And so it clearly leaves the unsafe region. So whereas if you introduce both, then, sorry, this one only has adaptive control, but it doesn't have, so it is able to follow the path, but it's not safe anymore because there is no way in which it can recognize that it is violating the state constraints. When you combine both, you can see that you are indeed able to do both. And I think in the interest of time, I do have animation, but I'm going to skip it and come back to it if we have time. Okay. So that's adaptation and safety. That says there is a way in which you can do both. And let's see if we can integrate it with optimality. So again, I want to bring back the notion of a reinforcement learning and combine the elements of what you can do, which basically tries to look ahead and have a notion of optimality so that you're minimizing this cost, even while you're staying stable, whereas the adaptive controller is online. So we've come up with an architecture that basically combines both, which basically relegates the role of a reinforcement learning based optimality based control to the outer loop, and the inner loop basically introduces adaptation, which again some very careful integration pieces. So here's the overall structure, and here we considered a nonlinear feedback linearizable problem, and so which then required us to basically identify what the underlying regressor is that we need to employ in the adaptive law. And with that, we were able to actually come up with a stable solution. So the task that we carried out in here is basically one where it's a quad rotor, and it's something that it has to land on a moving platform. And the reason why RL is a very suitable tool is because the cost function is not something that you can have a quantitative structure. It is more very unstructured, and so it says, don't crash, don't have too much of a variation in the XY plane, don't wobble too much, so the some of the Euler angles need to be constrained, etc., etc. And you want to make sure that you need to land within a certain time. So because of all of these things, then it turns out that you can use this RL structure and a very nice training procedure. And by doing that, you can actually carry out an adaptation and optimality. So I want to play this. Let's see how I would do this. So okay. So here is the quad rotor, and the one on with the white thing is the one that was incapacitated. And if you don't have, are you able to see the video?
Yes. Yes.
Okay. Whereas what you're seeing now is with adaptation, and what the adaptation is basically because the propeller blade is broken, and we deliberately broke it and stuck it with the duct tape, and in flight we basically introduced this parametric uncertainty. So that's what this is doing. And what this showed is that adaptation does work very well for these kinds of quad rotor problems. So that sort of gave us the starting point for the moving platform story. And again, here we introduced 50% loss of effectiveness mid-flight, just like what we had done with the video that you saw. And so what this allowed us to do, when you only have RL and you don't have this inner loop component due to adaptation, you're really not able to have the success rate that you want. In fact, in this particular case, it crashes. Whereas the adaptive controller is able to do much better and have not only make sure that it lands, but at the same time also do it in the requisite time, as is shown in these kinds of metrics. And we also compared it with other kinds of RL methods that have distributional shifts and domain randomization But in all of these cases, the advantage basically is that there is no need for training, and it allows you to actually get much better metrics with much less computational effort. So this is, and why this does it is basically because of the adaptation allowing us to keep track of the variations due to the errors in modeling. And what that does is it gives you a way of keeping track of the deviations from what the reference model is doing versus what the actual the system is, how the system is performing. And because of that variation, you're able to actually integrate the control, the actions better, and make sure that you really track well. So another example that I want to walk you through when it comes to integrating optimality with adaptation is this, again, problem that has been studied a lot in the especially in the last few years in the machine learning literature, that basically takes the very standard LQR problem that we know very well, where you've got measurement noise, and but on top of all of that, you basically have parametric uncertainties as well, and you want to basically stabilize it and converge to and have this optimal cost. So the structure of most of these algorithms basically is something that looks like this. So here is the inner loop, and you have a controller, and you have the plant, and the outer loop basically has a learning component. So essentially, you're taking all of this data and then using a least squares parameter estimator and come up with an estimate, and use that estimate to calculate the new feedback gain and repeat the process. And you basically calculate this feedback gain based on some sort of a metric, a threshold. And if you find that you have enough new information that comes from the underlying regressor, then you basically compute your A star and estimate of A star and B star, and therefore now you have a new gain. So right, very straightforward, something that is well known to many of us in the adaptive control community. And so the problem then is, so how do you actually make sure that this V sub t has got useful information? Then you need to introduce excitation. And they introduce excitation in the form of noise. And this is the exploratory signal. And so, I mean, there's another story I can tell you in terms of robust learning, but let me not go there. Let's assume that it's okay to do this, right? So there are all kinds of methods that have been proposed in the literature. But the problem is there are a few problems. The first is that you need to gather data for a while, right? And then, therefore, while you're doing all of that, whatever is the K sub t that you put in better be stabilizing. So even though you do not know A star and B star, you have enough information about it to say that, hey, here is a K that is going to be stable, right? So that's the one. But then, so which means obviously leads to the question, what if that's not the case? So that means we need excitation to learn very quickly and stabilize, right? So the question is it possible? So that's, you need that. So stability relies on excitation. Initial controller must be stabilizing. So these are already the first two problems. And the third one is that the problem, because your A hat and B hat may not be accurate, you want to really search for what is known as a nearby optimistic parameter. So this makes the optimization problem really very difficult. So the question is, can we develop an algorithm that doesn't require any of these things? And so this is our approach based on direct model reference adaptive control that allows you to basically come up with a way of designing a controller that really does not require the initial stabilizing things. You do introduce excitation, but it's a next step. It's not something that you are limited by. And then the RLS-based adaptive law basically gives you a way of introducing a procedure for calculating new feedback gain. And that in turn is utilized in order to calculate a new reference model, because you have new information and the system is different from what you thought it was. So it doesn't make sense to have the same target that you imposed where you assumed that your plant was in the nominal state. So then that in turn allows you to do better. And that's how you get to optimality. And this is the link that we have introduced, and it looks very exciting. And that is that here is a problem where what you're seeing on is that the tools which are regret with two different kinds of noise. And so the algorithm that we introduced And this basically is what Peter Fisher put together. And so what this says is that our approach is the green, and we do just as well when it comes to just basically looking at the regret and the state. But it is when it comes to the current literature, you're able to do much better compared to the current literature, and you get a much more optimal than before. So that's which is the red. So, and it also shows that the state magnitude stays much smaller when the initial feedback gain is not stabilizing. We also looked at a 6-DOF quadrotor, and here too, you can see that you're more optimal and your pitch angle stays smaller. And so these are the advantages of having this kind of a direct approach. So that's basically what I wanted to share with you. Adaptation and learning have a very rich interplay, and these are the different, there are all kinds of things that we need to watch out for. There are ways in which we can expand the scope of what we're trying to do with adaptation to include broader goals of safety and optimality, and there are ways in which we can actually stitch those together. And all of these are really giving us ways of expanding the scope of what we can do with adaptive control to include not just inner loop metrics, but also outer loop ones that give us ways of meeting stability and optimality. So in all of these things, I think one of the things that I really want to underscore is the fact that sometimes you really need to adapt first. You need to control first, and you need to have guarantees with imperfect learning. And learning is something that comes with hindsight. And so in order to really go towards fully autonomous systems, it is imperative, of course, which is something that we always do, that you have real-time decision-making tools with analytical guarantees. We also need to integrate with other building blocks, which is very, very possible. And sometimes it's not always learning for control. You do need to address control for learning and make decision-making under various timescales. And that requires a broader outlook. And that's something that's really important. And here's some of the papers that this was all built on. And I'd like to thank you very much.
Thank you very much. Thank you very much, Anu, for this very interesting talk. Oh, I can see questions already coming. Please directly unmute yourself if you have questions. I think very first one is Namhon. If you can directly unmute yourself, please. Okay, so Namhon has put a hand down. So, Miroslav, please go ahead.
Anu, thank you for such a nice talk and so many subjects covered in less than an hour. The part that interests me the most is safety with adaptation. I have not dared to venture into that subject. It seems very hard, and I wanted to ask you if your experience has been. It's a question of the level of intuition. There are technicalities underneath to support it, but is it your experience that, as in the paper of Ames and what's the name of the collaborator? Is it Taylor?
Yeah, Taylor. Yeah. Taylor,
Yeah.
I think.
Is it your experience that the results that exist so far require that the adaptation be made fast, and that some a priori knowledge of the size of the parametric uncertainty be available?
Yeah, you're right. So there are two things. One is those assumptions, that some requirement that it stay within a compact set, and the other is that your solutions are either going to be computationally highly intensive, that there is no guarantee that you'll be able to provide a solution in real time, and that you might really have a very conservative design which sacrifices performance goals for safety. Because if those constraints that you have to satisfy, essentially what they end up doing is that the constraints that you have to satisfy have to hold for every parameter estimate inside a compact set. So in order to do that, you really have to, and there are variations that the paper that Slotine has written as well. And so the way you cover that is by saying, okay, I'm going to assume the worst case uncertainty, and for that worst case uncertainty, these inequalities have to be satisfied.
Mm-hmm.
So if you essentially you have a very conservative approach, which will end up sacrificing performance.
Mm-hmm. Yeah, that's it. Somewhere closer to robust control.
Yeah, sorry. Let me add. Our approach doesn't do that. It's completely different. Yeah. Thank you. Sorry.
Yeah, we're used to actually not being subject to such high demands in stabilization. That's why it's disappointing that safety pushes us much closer to robust control than what we're used to adaptive control being able to do. Ideally, no assumption on the parameters, no requirement to update very rapidly.
Yeah.
Okay.
Yeah, I mean, so in the example that I showed you, we don't technically we don't require parametric uncertainties to lie inside a compact set. Mm-hmm. But as you know very well, when you introduce other non-parametric perturbations like disturbances, etc., then you need to, of course, contain your parameter search space, and that we would have to do here too. But in the most ideal case, if you're saying, hey, have your everything be stable, you introduce parametric constraints, parametric uncertainties, but you also have these state constraints, we can do it.
Thank you.
Thank you. Any further questions? You can directly unmute yourself, please. Oh, please. Ananda?
Hello, Professor Annaswamy. Thank you for the presentation. I would like to ask you about CBF. You presented it. And the theory in CBF says that the safe set will be foreign invariant if you grant the CBF condition. But in some cases, you are obligated, how can I say it? I face myself forced to start the system in a non-safe condition. So I have no guarantee that safe maintenance. I don't know if you have this situation, and I would like to ask you some intuition on how to recover the barrier condition in order to start the safe invariance guarantees.
Yeah, if you started an unsafe set, then already the problem is over, isn't it? I mean, so you're not safe anymore. So I'm not sure. So there must be some wiggle room for you to, I mean, this is like saying, come up with a control solution, but the system is uncontrollable, right? So then there's something wrong with the problem statement itself. So there's no solution. I'm not sure if that's what you meant, but so the point is that unless you have, I mean, there's some things that are like necessary conditions. So you when you start somewhere, if you're already in the very close to the boundary of the obstacle, then there's very little that you can do. So you assume that there's some sort of a dwell time, a distance between where you start and where the obstacles are, right? So if you already, like for instance, the missile dynamics, I mean, if you already are at the very close to stall, then you'll get there, unfortunately. So I'm not sure whether those are problems where, there are some problem statements that you simply need to have a well-posed structure. Yeah.
Anu, this was, if you don't mind me stepping in once more, this has been on my mind also. I call this problem rescue to safety, and I see it being touched by a few people, and the notion is that the initial CBF might be negative. The task of the control is twofold: to bring it to the safe set. Okay, not instantly, obviously. You know, it's like stabilization, except that it's a stabilization to the safe set, followed by the operation within the safe set. And for that to control, this is so
Yeah. So now I get it. So so then I think what we're saying is there's safety, which is the actual, system property that you want, and the mapping of that to h of x, right? So your h of x basically, so there's most certainly there is work to be done. What if your h of x is wrong and you need to come up with the ideal h star of x, right, for a given problem? That I think there's a lot to be done there, and we'll get there, but not right now. But yeah, you're right. You have to worry about that, and that proper I mean, you know, this whole business of, it's the same thing with Lyapunov functions, right? You start with a Lyapunov function candidate and you hope that that's the right one. What if you're wrong? You just need to figure out, and of course there are all these sum of squares and all of these different computational methods. There are computational methods where there's no guarantee. On the one hand, we've got Massera's theorem that says there is a necessary condition for the existence of a Lyapunov function. To go from there to actually construct it is a process. The same thing, I think, with also these barrier functions. Probably one exists for every safe system that is forward invariant, but to go there from wherever you are, I think requires some careful thinking. I don't know if that answers your question.
Thank you, professors.
Any questions? Any further questions? Tiago, shall I hand over to you now? If you open. There is a question in the chat window, actually. Could you please comment on how understanding adaptive control as a solution to infinite horizon nonlinear optimal control problem has implication to robustness?
I think the question is whether you are able to, I think it's really a question of the interplay between optimality and parametric uncertainty. So when your models have errors, then your HJB equation is going to have problems. And if your HJB equation has problems, then you need to come up with a way of approximating whatever the underlying nonlinearities are. And our go-to tool, by and large, in the approximate dynamic programming world, is reinforcement learning, which then brings us to what kind of analytical guarantees do you have when you have neural networks? And so they're all sort of mixed together. And I don't know of any results that tell you how you can make that problem analytically more tractable with guarantees when you have infinite horizon versus, again, it could be that there are some there that, in which case, I apologize. I'm not familiar with what, if any, are the intersections, the bearing of the infinite horizon to making the approximate dynamic programming problem more tractable. I don't know if anybody in the audience knows it, then please do chime in, but I don't know of any.
Thank you. I hope that answers this question. So, Tiago.
Bing, can you hear me now?
Yes, they can now.
So thank you, Anu, for saving some time to spend with us with this nice talk. So I have one question. Maybe it is a naive question, but of course, probably you have tried delays in some sense. I was curious about the possibility of considering the CBFs under delays, if you have already checked it or thought about that. Have something to say?
So when you say delays in where? In what?
In the measurement.
Okay.
Or even in the control signal, when you try to actuate.
Okay. So, well, yeah. So this is probably something where Miroslav's PDE tools might be very relevant. We've done a little bit of work on adaptive posicast control. That might be also come in here. We're just getting started with this whole CBF with that adaptive thing. This is our very first step, which is, you've got this problem. States are accessible. How would you do that? And then, of course, the next step would be output feedback. The next step would be what you have with time delays. But I don't see why, because this design is very modular. Because it's very modular and we've got the right pieces in the adaptation and the right pieces in CBF and the right kind of integrative piece, the coupling terms are picked carefully, and all of these things basically help us expand the scope. So because it's a very modular procedure, and the most important difference between what we have brought in versus what's been done before is that the structure of the CBF filter is based on the reference model, not on the plant. And that's the biggest difference. And because it is that, that's what makes it modular. And because it's modular, it seems to me that the adaptive control design is whatever it is of your choice. You know, it could be your ES-based stuff, or it could be Miroslaw's PDE-based things, backstepping, or it could be adaptive posicast. But whatever is requisite, the requisite control, adaptive control structure that is dictated by the problem, right? Are states accessible or states are not? Is there a time delay? Do you bring in robust, you know? Once you do that, it seems to me that that together with this pre-filter allows you to basically do both, I think. So I think it should be positive. I mean, overall, this is right. I mean, adaptive control has focused on inner loop. Well, rightly so, right? That's the first sort of battle that you have to find. But then what all of these pieces do is to allow you to expand the scope of adaptive control to outer loop as well. So we've never really bothered about what exactly are the exogenous signals. Now, if you can design them using CBF, great. Then we will use that in combination with adaptation. I don't think it's just a stapling together of solutions. It's the right marriage between all of these tools, which I think is what we're trying to do.
Thank you, Anu.
Thank you.
Thank you. And I think, Tiago, shall we conclude, we have the time, shall we conclude the session?
Yes, I think
okay.
It was a wonderful section. And I have to thank you, all of the audience, for being in this nice talk of Professor Annaswamy. And we'll have more in the next week. I will give the information today. So thank you, Anu, for everything. And I hope to see you all in the next.
Yep, absolutely. And thank you all for dialing in from wherever your time zones are, whether it's too late or too early. Thank you all. And again, thank you, Tiago and Bing, for this invitation. It was a pleasure.
Thank you.
See you guys.